We are still on geometric sequence, and we are studying the sum of a geometric sequence. Is it even possible to get the sum of all the terms in a geometric sequence? So, given a geometric sequence, when we aim to get the sum of the entire sequence, we will come up with a new sequence, and we call that sequence the sequence of partial sums. So let's say, for example, these are the terms of our geometric sequence. Let us get the sum one by one. So the first sum is a sub 1. We call that S sub 1. The second sum is a sub 1 plus a sub 2. The third, the fourth, and the nth sum will be given by this. So let's say, for example, this is our geometric sequence. What is the common ratio, by the way, of this sequence? It's 2. Let us add the terms one by one. So the first sum is 1. The second sum is 1 plus 2, that's 3. The third sum is 4 plus 3, that is 7. The fourth sum is 8 plus 7, that's 15. So our new sequence, which is a sequence of partial sums, is 1, 3, 7, 15, so on and so forth. From our previous video, we presented Theorem 2.4, the sum of an infinite geometric sequence. It is possible to get the sum of an infinite set. We must pay attention to the value of the common ratio. If the absolute value of r is less than 1, the sum of the infinite geometric sequence is this: a sub 1 over 1 minus r. On the other hand, if the absolute value of r is greater than or equal to 1, the geometric sequence has no finite sum. If the common ratio or the absolute value of the common ratio is less than 1, the sequence of partial sums is convergent. It is converging to a finite sum. On the other hand, when the absolute value of your common ratio is greater than or equal to 1, the geometric sequence has no finite sum, or the sequence of partial sums is divergent. Example: this is a geometric sequence. The common ratio is 2/3. Let us produce a few terms of this sequence. So the first term is 3. Then we multiply it by 2/3. That becomes 2. We multiply by 2/3 again. That becomes 4 over 3. So that is how you generate the terms of a sequence. The common ratio is 2/3. So that is less than 1. This graph is the graph that shows the sum of our geometric sequence, of the terms of our geometric sequence as a function of n. When n is 1, the first sum is S sub 1, which is equal to 3. When we add 2 to 3, it produces a new sum, which is 5. And we add 4 over 3, that gives us another sum, so on and so forth. And so our sum is increasing because these terms are positive. So when we keep on adding a positive term to something which is already positive, we expect the sum to be increasing. But this sum does not increase indefinitely. There seems to be like an invisible barrier here, an invisible boundary. And if this is how our partial sums behave, then we say that the sequence of partial sum is convergent. How about when we have this geometric sequence? The common ratio is 3/2. It's greater than 1. These are a few of the terms of this geometric sequence. So coming from 3 or beginning from 3, we multiply by 3/2, that is 9 over 2. We multiply by 3/2 again, that's 27 over 4. So that is how you produce the elements of a geometric sequence. Let us get the sum of this sequence. Does it even converge to a particular sum? Well, the theorem says no, it does not, because the absolute value of your common ratio is greater than 1. And in fact, this is how the partial sum behaves as a function of n. So you can see here that this sum is quickly rising up. So this means the sequence of partial sum is divergent. This sequence or this geometric sequence does not have a finite sum. So these are the things that can happen to a geometric sequence when we are computing for the sum. The sequence of partial sums can be converging to a particular real number, and that happens when the absolute value of your common ratio is less than 1. So when the sequence of partial sums behave this way, if it tends to settle at a particular value, then we say that the sequence of partial sums is convergent. However, it can happen that the sequence of partial sums is not convergent. It is divergent, and it can happen when the absolute value of your common ratio is greater than or equal to 1. When that is the case, then we say that the geometric sequence has no finite sum. Its partial sums can go on increasing and increasing towards a positive infinity. It can also go on towards negative infinity, or the partial sum keeps on changing its value. It seems to be oscillating between 2 points, in which case it does not settle at a particular finite sum. We describe this sequence of partial sum to be divergent. Okay, so let us determine if the following geometric sequence is divergent or convergent. We will look into the common ratio. So that is the key. This one is a geometric sequence. The common ratio is 1/3. It's less than 1. It is convergent. The sum is convergent. It has a finite sum. How about this one? Another geometric sequence. The common ratio is -0.5. Its absolute value is less than 1. Again, it has a finite sum. The sequence has a finite sum. The sum is convergent, or the sequence of partial sum is convergent. How about this one? This one is an alternating sequence. Alternating sequence has something to do with the alternation of signs. Negative, positive, negative, positive. So this one is also a geometric sequence. So what do you think is the common ratio? Well, the common ratio is -1. You pick any pair, you get the ratio, it's -1. And the absolute value of -1 is equal to 1. So this means if we were to get the sum of this geometric sequence, that sum does not exist. It has no finite sum. Or we say that the sequence of partial sums arising from this sequence is divergent. This is the general term for this geometric sequence.